Sorry about that. I got a message, a little pop-up thingy saying that my stream quality was going to crap. So I just started again with a lower bit rate. Hopefully it's fine. Back to where we were. So this program is still running. If it's still running, that might actually mean that we've hit an annoying bug in the Studio UI. So actually, when I run this is a Pharaoh Smalltalk, and when I run sub processes calling out to Nix here, occasionally they just seem to get stuck for me at a certain point, and I don't know how to fix that. So what I normally do is just um, start over. Let's see if that's what's going on here. Looks like it. I'm just going to restart this because I've been running this instance for probably a week or something, so it's not the end of the world if I restart it this time. So let's pull up a shell. That was connecting to VNC display number 6. Let's start a new instance. The way you run Studio, or the way that I run Studio anyway, is like this. I log into a Linux server where the GUI runs, and I tell it to please run on a VNC with a VNC endpoint. That's VNC endpoint number 7. Away it goes. So now I can hop over here on my Mac and connect there and get the GUI. So the GUI always runs on Linux. It runs on a big beefy server, and then I access it from whatever is convenient. Which for me is oh no, I know I did a copy paste failure there. I'm going to open up the other one as well so I can get my script back. It's a good thing that I left it running. Copy that, and I'm going to paste it there, and then let's see what happens here. And we'll resize this to cover the desktop. Okay, so I did have an error. I've got dreadful, as I said, dreadful error reportage. So I will just dive in and find. This is the terrible case where you see the price I pay for not putting in good error reportage when Nix reports a build error. It just kind of dumps me in the debugger for the front end, which is not very nice. But one thing at a time. It's a bit better. So okay, that code ran. This is an inspector looking at the data that was produced, the side effect of executing that. So this is something that the JIT came up with. We have the events that happened in the JIT when it successfully traced something, when it aborted tracing something, and we have the profiles here. So okay, I just want to have a quick tour now of what we can see here, and then think about how we could present this in a source code view. So that's the big thing that's missing, is to take data from the JIT and then cross-reference that onto the source code, so you can look at the code, look at the source code, and see what the JIT did with it. So at the moment, anyway, we have a profile, one profiler set. All of the machine code was generated from a complex of traces. They're called, starting at line 7 of the script. And if we look there, we ended up with 3 traces. We had a looping root trace, and that was from line 7, which is going to be this one. So I mean, I know what this is going to be, right? So this is the first thing that compiled for the first 1,000,000 iterations. That's this one here. Then for the other 9,000,000 iterations, we took a different branch. Whoops, I shouldn't hop over there. Took a different branch. We didn't take the if, we took the else, and that means that we're going to get separate machine code for that. So that'll be this second trace on 911, 4 lines later. Yes. And then finally, we had another trace that enters the interpreter, which basically just means that it took another branch that was not able to just-in-time compile. So that's this one here. So this was another path that came later. And we can see also a little bit of profiler information there, which I think is interesting anyway. We see that this one, the first trace, which is the first loop, ran 100% machine code. The second one also ran 100% machine code, and the third one, last one, ran in almost a tiny little bit of machine code, which is probably just the code that's generated for branching out of the out of the kind of the JIT machine code mode and into the VM, and then in the VM in the garbage collector. Because we're just assigning, building a closure and putting in a global variable all the time. Anyway, I would like to be able to get kind of all that information without necessarily having to go through this. This is like a low-level detailed view in my mind. I would like to be able to see most or all of that information just by glancing at the source code. So the question is, how could we do some syntax highlighting that would make this transparent? So I think it's time to go into kind of fantasy mode, where we just take the Lua code here and copy paste that into a text editor, and just I had an idea this morning for what we might be able to do. Do we have any fixed font there? God, what's the name of it? Corey is fixed, isn't it? Okay, so excuse my font selection. How would we make this? How would we update this code to reflect what the compiler has done? And I would say the first thing here, this first loop here, it didn't appear anywhere. We didn't see any information about that, so there was no JIT activity here. It only ran 10 iterations, and it actually takes more. It takes about 30 or something before a loop would become a candidate for just-in-time compilation. So I would like to de-emphasize this code because it's irrelevant to the JIT, and I would imagine we could do that by graying it out a bit. So let's do that. So now we've kind of made things a bit more meaningful. We look at the source code and we say, okay, well, I know that this didn't matter. That code is free to ignore. Then the next thing is, what I was thinking is for each line here, one at a time, we would just go into the JIT structures and say, well, what happened with this line? Was this line somewhere that the JIT stopped making? Was it somewhere that we started making a compilation attempt? Was it somewhere that we successfully completed a compilation attempt? Was it somewhere that we aborted a compilation event? Was it just another line of code included in a root trace, or was it a line of code included in a side trace? There's a lot of different ways that a line of code can be compiled, and the same line of code can be compiled several times as well. So it would be nice to come up with a way to annotate on the source code just the way that the lines of code were used. And it would be great if some of these were orthogonal, so that if the same line of code, for instance, is in a looping root trace and a non-looping root trace and a side trace, it would be nice to be able to kind of see all of those things. Maybe, unless it's too much information. I don't know. Let's have a muck around and see. So the first thing is, we know, if we hop back for a second over here and go back to, sorry, that's the wrong one. That's the right one. Okay, so this information here that we got there, our first trace compiled into a loop, and we can actually see, if we dive in here, we can actually see every single line of code that executed for the compiler. So this would be the basic source of information that we have for doing source code annotations. So if we would look up what happened on script.lua line 13, we could say, well, this was a line of code that was compiled into trace number 1, which is a looping root trace. So what we could do is just loop through all of these lines of code, and then in the source file we could annotate those. So let's just do exactly that. We take this, see if we can get everything on the screen at once. Okay, so we have line numbers here. In case you were wondering, I don't normally use this text editor. I don't know why I chose it. Anyway, whatever. So what we want to say is that the first it's quite interesting. Okay, so the first trace is going to represent a full execution of this loop. So it's going to represent the path of control that the first million or so, I think it was, iterations took. So it's gonna get this line of code. It's gonna say, yes, I execute the then branch because the loop index starts small, which causes that to happen. And I'm gonna make this bold, And bold is going to mean for today that code was compiled into a looping root trace. So this is the code that is the most optimized, actually. So the code that comes up in bold is going to be the stuff that the JIT was selecting for the most aggressive optimization. So then it's going to get down to the else. It's not going to have included the else. So if we look over here, yeah, we see a hop. It goes lines 8 and 9, which are going to be this and this. And then it hops over a few, which is going to be the else and end. That doesn't, and then it runs down here, and it's going to execute this line, which is the test to see if we're near the end of the loop, because it has to do the test, right? Even though we're not at the end of the loop. So I'm going to make that bold. And then it's not going, so this must be line 13, and we don't see line 14 there. So it didn't execute this because this is the way that we compiled the early iterations of the loop, and in that case we always take the then branch on this, and we don't take the inside of this because the loop index was not above 9 million. So that now is annotated to show this first trace. Now we know that we got a looping root trace because we see some stuff in bold, and we can see which lines of code were the most aggressively optimized. And then the next thing that we're going to want to do is to show, well, the next trace, which is this one here. So again, it would be nice to have line numbers, but we can kind of figure it out. This was line 13. This must be line 11. So the big difference here is that the side trace, so this trace number 2 is a side trace. So the original code, the originally compiled code represents a whole trip through the loop. And what happens with the side trace is we get a part way through the loop, and then we hit something that is different compared with the code that we had already compiled. There can either be a difference in a type of something, like something that used to be an integer is now a string, or in this case it can be a difference in branch behavior. It can be a branch that previously took a then and now took a else. That's what we have. So what we have is it executes line 11, hopping back to our text editor. I'm going to make this italic to say that it's included in a side trace. The italic, it doesn't stand out that much actually making it italic. I might, in that case, do something different. Let's make it blue. No, that's the wrong blue. Let's make it this. Okay, that's code that ran in a side trace. And we see here it also does this line 13 down the bottom. So this actually tells us something interesting. So on the side trace, it didn't run any of this code up here, and the reason for that is that the root trace, the first trace, starts executing here, and it comes down to here. No, sorry, the root trace is executing here, and if this condition holds, then it goes in here. But with the side trace, this condition didn't hold. So what happened was, sorry, going back to the very beginning for a minute. It takes a while to figure out the right way to explain these things. This loop runs 10 million times. The first million times takes this branch, and the first machine code, or the first JIT code that was generated, corresponds to that case. So it generated code that was specialized for taking this branch, and that's what we put in bold. And the next thing that we're looking at now, that I'm kind of doing with colors and italics, is the second trace, which is for the millionth and after iterations. So as soon as the loop index gets over 1 million, then we don't take the then branch anymore. That's kind of done. From that point on, we take the else branch, and that means that we can't keep executing the code that we compiled the first time, because that was specialized for this. It inlined everything there. So that's why the code, when we enter the loop on the millionth, or after millionth iteration, it starts off here on the main, on the original code that we generated, but then it detects that this branch we're not gonna take the then, so we can't continue on that code. So we need to then branch off to a so-called side trace. So we've already executed this line of code, that's done, but then we leave the first root trace and we go off onto this second side trace. So what I'm trying to explain here is why over here, when we look at the side trace, the first line of code we see is line 11, which is this one. So on the side trace, we see that, and we see line 13, which is down here. So basically, we've started, this trace is starting from the middle of the loop. It's starting from after we've tested this, and then it compiles everything else that needs to happen then to get through to the end of the loop. So okay, we executed that already in the root trace. We don't need to in the side, but we do need to run this, which is our line 11 over here. And then we also do need to run this, which is our line 13. And actually this part down here, the code in the side trace and the root trace is going to be the same, because in both cases we're not this if is going to evaluate to false, because we're not at the 9 millionth iteration. And I apologize for the different ways I've written these constants. Anyway, so even though that part is going to be the same, it has to be compiled separately, because once we've veered off to a side trace, then we're not going back on the root trace. You never go back. So the root trace goes around in a loop, and if at any point it can't follow the path that it chose originally, then it goes off to the side and it continues down, and then once it gets to the end of the loop, then it can kind of start again on the original path and go around again. But it can't kind of go back and forth. You kind of just make a tree here of all the different paths of control that need to be compiled. Anyway, so what that means is that this line of code here is compiled both into the root trace, which is why we already have it bold, and it's also compiled into a side trace, which is why we're going to color it. So whether this is going to be too much information in practice, I don't know. Let's make that the Docker Blue as well. Whether this will be too much information in practice, I don't know. So it is kind of legitimately it is legitimately interesting to know that this is both code that runs in the root trace and also code that runs in a side trace. So to start with, we do it like that. Anyway, we had 3 traces compiled. So we also had this last one here, which exits into the interpreter. So it actually didn't manage to execute any bytecodes. So this trace exists purely to get out of the JIT machine code realm and go back into the bytecode interpreter. So it's empty in the sense that it doesn't execute any Lua code, because it just bails out so that they can be executed in the VM instead. But in any case, we can see that it's on line 14 that this happens. So it would be nice to know that. Sorry, going back to our editor. It would be very interesting to know that here, that this line is a point where we bailed out of JIT mode, where there were some failed attempts to compile the code, and that could be done. Let's make it red, for example. Would be pretty neat. So now this is some marked up source code that contains all the information from the set of traces that we have, which what kinds of traces they are. This one was a looping trace, this one was a side trace, and this one was a bailout to the interpreter. And it just relates all of the source code lines to the way that they were compiled. So I would hope that if we would just look at this for the first time without having seen any of the other stuff, this would actually be able to tell us some things. We would say, okay, this is all grayed out. Maybe for effect we can compare this. Hold on a moment. Let us put the unhighlighted one over the side for comparison. I don't know if this helps, but can't hurt, right? We will just make that all non-bold and all the same color. Okay, so for the purposes of comparison, the one on the right is the source code, where we're kind of left guessing. We don't have any idea how it compiled. And this one over on the left then is where the marked up one. So the question here is, would this be useful? Would this tell us some things? Should we update the user interface to automate this this kind of markup? So we would then, in this case, we could see here, this is grayed out. We don't even need to give that any thought. Well, it hasn't been involved in any JIT compilation. If we think that that's suspicious for some reason, then we should give that some thought. But in this case, okay, it had a low iteration count. It's obviously not. It only ran a few times. It wasn't worth compiling. Fine. Then we get to this. Then we get to this loop, and we see that this was the branch in bold that was optimized most aggressively. The reason for that is actually just that it was the one that came first, that was compiled first and got priority. So actually it's kind of useful because you're not born knowing that this is how the JIT compiler is selecting things to prioritize, that it's, you know, kind of the code that it sees first will get priority. So I think it's kind of really nice to have that spelled out explicitly. This is the code that got optimized most aggressively. Then we see on this line that, hey, that line also did execute because it's not grayed out, and it is not bold, so it didn't execute in this looping root trace. It execute, and it's colored, so it happened in a side trace. So that's nice to know. So we can tell that this line of code represents a code path that was not as well optimized as the other one. And down here we can say the same thing, well, almost the same thing about this line. This line is bold, so it did execute in the looping root trace. So it did run in a very aggressively optimized root trace because it's bold, and it also ran in a less aggressively optimized side trace because it's blue. So that line of code was compiled twice. And there's no kind of machine code sharing, so that was compiled twice. And generally speaking, the JIT can compile the same line of code any number of times, and it does a tremendous amount of inlining and so on. So that's absolutely something that happens. Then finally, we see that this line is something that couldn't be compiled, that forced an exit from running highly optimized JIT machine code to exit from that out into the bytecode interpreter VM, which is actually really good to know. So if you see a red line in your program, then you need to think about whether that's okay. Whether, you know, because that line will run very slowly. And so what we've seen here actually, I think, is quite a nice overview. So I think this will be great. Just my gut feeling. I think if we would spend some time to make the tooling do this kind of highlighting, and then be able to look at real programs like Snab, it would be actually, I think it would be quite awesome. And then if you would be able to compare, somebody complains and says that the program ran poorly on their workload with their configuration and that kind of thing, if you could load this up and see this visualization specifically for their execution based on the logs that were generated by the JIT when it ran their program, and then you could compare that with, you know, your known good expected behavior from a continuous integration or something, I think that this would be super cool. This would make a lot of stuff that is hard today easy, and then we could do more of it, which would be awesome. The thing that's lacking here, which is not necessarily a problem, is just, so we see a line in red here to say that it couldn't compile, but is that a problem or not? Maybe. So it's only a problem if it spent a lot of if it used a lot of CPU, right? So it's nothing is. This is why you need to cross-reference everything with a profiler. There is no point optimizing, you know, the idle loop, so to speak, the code that isn't supposed to be fast, that seldom runs or whatever. So that's where we would want to pop over. Before we would spend a lot of time trying to fix that red, make that go non-red, we would want to have a look at our profiler and see, you know, what really happened. And the way that I'm presenting it in the profiler now is just with a sample count. So the root trace ran for 24 samples, the side trace for 36, and the interpreter mode ran for 58. Okay, so yeah, the hottest bit of code was the one that executed out of the JIT code, and that is kind of interesting actually, just to reflect. It takes some practice to interpret JIT code, because on every trip through the loop, we start in trace number 1. That starts at the head of the loop, and we either stay on that all the way through, or halfway through we hop out to trace number 2, and then we might go all the way through and then back to trace number 1, and then, you know, out to trace number 2 in this kind of pattern. Or finally we might where's my finger? We might start in trace number 1, go down, side exit to trace number 2, go down, side exit to trace number 3, which then exits out of the JIT code and into the VM. And the thing there is that in the in the bad case where we exit all the way out, we're actually running all of these scenarios. So we start on trace 1, then we continue on trace 2, then we exit to the interpreter on trace 3. So what that means from a profiling perspective is that the root trace is going to get a lot of samples will be attributed to the root trace, because it's every iteration starts on that trace. So even if it branches off other places, the initial instructions execute there. So we can't. So these are not really disjoint, is the thing that I'm trying to say. The code is all a bit overlapping. Each iteration of the loop, we run one or more of the traces. It's not just one, and which is potentially a little bit confusing, but there you have it. Anyway, looking at this, I would say that this is a problem for that program. We spent a lot of time on this exit to the interpreter, and what that means is the profiler woke up. It said, the profiler wakes up every millisecond, which is on an iTimer, and says, what am I doing? Who's to blame for the fact that I'm running right now? And if it's inside the bytecode interpreter, it will look at the machine code trace that ran most recently. And in that case, it's this trace number 3, because since that's the one that exits back out into the interpreter. So I think this looks very, 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 very promising. So the topic of a future live stream should be to actually implement this so that when we have some so that when we would click here, we can see that this code started on script.lua line 7. I'd like to be able to click there and I'll click somewhere, and I'd like to be able to pull up the source code here, and I would like to see the source code annotated the way that we did it by hand in the text editor over here. So this is have to think about colors and bolds and all of that kind of thing, but basically I think that this is something that we want to have, and we should really do. It would be really cool. And one other thing that I just want to throw in, because I'm going to wind up soon, because it's New Year's Eve and people are coming for lunch soon, is that we have a bit of information here. So this was a bit of a simple program that didn't have any subroutines. So let's try just briefly another one that does. So if we would say let's get rid of the old code. We don't need it. For I is 1, 2, a big number. Do, and we say foo, and we say bar, and then here we define those. We say function foo is x equals string foo, function bar is x equals bar, whatever. Just assign the value to a variable. So if we would then run this program and give it a moment to run, and hope I didn't do an embarrassing syntax error, which I did. Before I open that debugger, let's just see if my mistake hops out. Function foo. See the mistake there? Let's actually have a look then. See what. Let's go debug. I really need to put proper error reported in here. At the moment, I mean, it's shelled out to Nix, and I'm going into the Smalltalk debugger now to find the string, which is the output from Nix, to see what happened. Do expected near foo. Do expected near foo. Hold on a sec. I think we'll take this next time. The kids are getting a little tired, ready for a nap. We've got a 2-year-old and a 3-year-old. They need a bit of attention. So this is weekend home office mode. Thanks for tuning in.